In Chapter 18, we will be looking at a special functional group in organic chemistry, and that's known as the carboxylic acids. So in this lecture, we will be looking at the functional group and different ways of representing the carboxylic acid functional group. Next, we will look at the nomenclature of carboxylic acids. Of course, you will recall that in chemistry we have a systematic way of naming compounds based on the IUPAC rules, International Union of Pure and Applied Chemists. Next, we'll concentrate on the physical properties of carboxylic acids. Then we'll look at fatty acids, they are really carboxylic acids, but long chain carboxylic acids, and their relationship to soap. Then we will concentrate on the chemical properties of carboxylic acids. And lastly, we'll look at the reactions. There's some reactions that carboxylic acids are involved in. So let us begin. First, this is the carboxylic acid functional group. But as you know, in chemistry, we have different ways of writing different molecules. So here's one representation. It has a carbonyl functional group, a carbon that's bonded to an oxygen in a double bond as shown here. And this carbon that's bonded to the carbonyl, if it's bonded to an OH, make sure it's an OH, has to be an OH to be a carboxylic acid. So this is one representation of a carboxylic acid. Here's another, where this OH here is just written as OH. Another one that we'll see is COOH. So if given in this format, you should know that this is the carbonyl right here, carbon, and of course this oxygen is this, and here is our OH, which is really right here. And the last representation that's used a lot in organic chemistry is right here, CO2H, where these two oxygens here are represented by that 2. So look out for that and be able to recognize these as carboxylic acid functional groups in organic molecules. Carboxylic acids are found in many compounds that are used in everyday life. And here are just some examples. Naproxen, used as an arthritis treatment. Here is the carboxylic acid functional group. Of course, here's the rest of the molecule. Another one that we've seen before is ibuprofen. Here is the carboxylic acid functional group. Notice it's written a little differently in this molecule. Here is acetic acid, which is the main ingredient in vinegar, as we all know. And here is it written in this format, the expanded format. And of course, here's aspirin, an analgesic, a painkiller. And here is the carboxylic acid functional group right here. So look out for those, be able to identify those. Next, we will look at the nomenclature of carboxylic acid. Looking at the nomenclature now, which is the IUPAC system. I hope by now you recognize why it's called a systematic way of naming compounds, because the system is basically the same, just a few minor changes. So let's look at naming this molecule here, which of course is a carboxylic acid. So of course we have to number so that we can get a parent or root name. So here's 1 carbon, 2, 3, 4, 5. So we have 5 carbons. Where do we start numbering? We start numbering at the end. That is the carboxylic acid. So the correct numbering system is 1, 2, 3, 4, 5, as shown here. And the incorrect numbering system is right here. So always start at our functional group, which is right here. So once you have determined how many carbons, that becomes the root alkane name. Once you have identified that, change the E of the alkane to oic and add the word acid. So the word becomes alkanoic acid. In this molecule here, we have 5 carbons. So therefore, the root name would have been pentane. Would have been pentane, but we changed the E to oic and add the word acid, so the name becomes pentanoic acid. Here's another molecule. This one has 6 carbons. Of course, as you know, if there's 6 carbons, the name becomes hexane, but we change the E of the hexane to oic, and it becomes hexanoic acid as shown here. Let us look at branched or substituted carboxylic acid as shown here. So here we have a branch, and here we have a branch. And of course the main chain has 5 carbons. So as we can see, that becomes pentanoic acid as shown here. There's a branch here as a methyl group, and there's a branch here which is a methyl group on carbons number 3 and 4. So the name becomes 3,4-dimethyl pentanoic acid. Here's another example. The root again is 5 carbons. So that becomes pentanoic acid again. And here we have an ethyl, 2 carbons, and a methyl, 1 carbon, on carbons 2 and 3. Since E comes before M, we start the naming with 2-ethyl and 3-methyl pentanoic acid. Let us turn our attention now to the physical properties of carboxylic acids. As we have pointed out before, there are different bonds in the carboxylic acid functional group. So let's look at acetic acid here. Here's the CH3, here's the carbonyl, and the OH. Expanded, it looks like this. So that's the CH3 right here. Here's the carbon-oxygen double bond. Here is the carbon-oxygen-hydrogen bond. These are all polar bonds. So this oxygen here is partially negative, and this carbon is, of course, partially positive. This oxygen here being electronegative is partially negative, and this hydrogen here being electropositive is partially positive. So you can see here there are at least 3 polar bonds in the carboxylic acid functional group. As you can expect, this will have a major effect on the properties of carboxylic acid. So let's see what happens. For carboxylic acids, it's possible to have hydrogen bonding like this. Here's a hydrogen of the carboxylic acid, of this carboxylic acid over here. And here's the oxygen of the other carboxylic acid over here. So here's the hydrogen bond. What's unique about carboxylic acids is that they form dimers. So here is the carbonyl of one carboxylic acid, and here is the hydrogen of another. So we have a nice dimer here. So this is an effective way of hydrogen bonding between molecules of carboxylic acids. Hence, as you can expect, this increases the boiling points of these liquids, because these hydrogen bonding here, they must be broken in order for vaporization. So let's look at this table here. Notice that this is a carboxylic acid, acetic acid. Here's an alcohol, and here's an aldehyde. All have just around the same molecular weight, but look at the carboxylic acid. The boiling point is 118 degrees C, whereas the others are far less. Likewise, the solubility in water. Of course, as you will recall, the solubility in water depends on hydrogen bonding to water, which is also a polar molecule. Very soluble in water, whereas the aldehyde is not as soluble. Just a couple more examples here. Butanoic acid, molecular weight here, all the same as these compounds here, except this is an aldehyde, this is an alcohol, and of course this is your carboxylic acid. This has a boiling point that's much higher than these. Let's turn our attention now to fatty acids. What are fatty acids? Fatty acids are long-chain carboxylic acids that are derived from animal fat, vegetable oils, and phospholipids. But the main aspect here is that they are carboxylic acids, number one, and that they are long-chain. What does that mean? Here's some examples. Here's the carboxylic acid, and notice this has 10 CH2s. That makes it a long-chain carboxylic acid. It's described as saturated here. Why? Because all the carbons are bonded to hydrogens and carbons which contain no double bonds. The unsaturated, on the other hand, as you can imagine, they contain double bonds. As you can see here, here's a carboxylic acid functional group. And of course here is 7 and 5, 12. 12 carbons, makes it a long chain. But it has here a carbon-carbon double bond, which makes it unsaturated. So these are described as unsaturated fatty acids, and these are described as saturated fatty acids because there are no double bonds in these. Some of these names you will be familiar with, like lauric acid and stearic acid. Those are saturated fatty acids. Examples of unsaturated fatty acids: palmitoic acid, oleic acid, etc., are unsaturated fatty acids. But the main point here is they have long chains bonded to the carboxylic acid functionality. So, to summarize here, so fatty acids, as we have seen here, they are most abundant will be animal fats and vegetable oils. To date, there have been about 500 fatty acids that have been isolated from natural sources. Most have between 10 and 12 carbons, which makes them, of course, long-chain fatty acids. They are mostly unbranched, so they are just long-chain fatty acids. No branching, no ethyl or methyl groups bonded to that chain. Here's a key. Most of the unsaturated fatty acids are the cis isomer. So now again, you should relate our previous knowledge of cis and trans double bonds. So for unsaturated fatty acids, most are the cis isomer and not the trans. We'll see an example of that in a second. So let's look at unsaturated fatty acids and the melting point compared to saturated fatty acids. So here is a saturated fatty acid. Saturated because all these carbons here, there are no double bonds in this long chain. Down here, however, there is a double bond, so this is an unsaturated fatty acid. Here is another example. There are two double bonds, so this linoleic acid is classified as an unsaturated fatty acid, as shown here. Here's another example, three double bonds. Notice again that they are cis double bond because the hydrogen here are on the same side as this carbon. And of course the alkyl groups are on the same side. Remember, cis here means same. So these are cis unsaturated fatty acids. Let's see if we can rationalize here the melting points. Notice for the saturated fatty acid, the melting point is 70 degrees for this molecule. Pretty high. But if we look at the unsaturated, it's 16, much lower, -5 for this one that has two double bonds, and -11 for this one that has three double bonds. So from this, the observation is for saturated fatty acids, the melting point in this case is pretty high, whereas for unsaturated fatty acids, the melting point is much lower. Let's see why. For saturated fatty acids, they can align themselves like this in a very structured manner. Of course, as you know, to melt a solid means that we'll have to supply energy to break the interactions between these two molecules or between these molecules. That requires energy, so the temperature here is, it requires a higher temperature for melting. So therefore, the melting point of saturated fatty acids are pretty high because of the structured arrangements here and the amount of energy required to melt these or break the interactions here, mostly London forces or Van der Waals attraction. It requires energy, hence a higher melting point. Let's look at the other structure here. Unsaturated melting point, unsaturated fatty acids, pardon me. Look at this. Here is the unsaturation. It causes this molecule to have a structure that's not as organized as the saturated ones. So because it's unsaturated, the packing is not as efficient. So therefore, the bonding between two molecules here are not as good as for saturated fatty acids. Therefore, it requires less energy to melt this. Therefore, the melting point of unsaturated fatty acids are much less or less than that of saturated fatty acids. So that's the conclusion there, is that the melting points of unsaturated fatty acids are lower than the melting points of saturated fatty acids. Okay, let's go into soaps. What are soaps? Again, let us define soaps, and then once we understand what soaps are, let us see if we can apply the concept of soaps and its effectiveness in everyday life. Soaps are defined as the sodium and potassium salts of fatty acids. Remember, fatty acids here are long chain carboxylic acids. Soaps are prepared by a blend of beef tallow and palm triglycerides. We'll see what triglycerides are in a second. They're just, as the name implies, tri, so it's three fatty acids that are linked together in one molecule. As shown here, triglycerides are triesters, so they're bonded by ester functionality. And solid fats are melted with steam, and the water of insoluble triglycerides form and are removed. So in other words, this is how soap is made, as shown on the next slide here. So here's a triglyceride. Again, as I mentioned, tri here means three. So 1, 2, and 3. And here's the ester functionality. Here's one ester, here's another ester, and here's another ester. Remember the ester functionality that we did way back when we did functional groups in organic chemistry. The reaction with sodium hydroxide or potassium hydroxide, heat that up. The process is called saponification. What happens here is that we liberate here 3 moles of fatty acids. But because this is a base, we have here a salt. So we have here sodium salt of the fatty acid. And that is described as soap. That is the sodium soap here. So again, so this is basically the soap. It's the salt of the long chain fatty acid. Let's see how it works. So here's a long chain. That's just symbolized here by this. And notice it's saturated, so it's a nicely organized chain of carbons and hydrogens. As you can imagine here, since these are CH2, CH2, CH2s, they are organic, so therefore it will not be soluble in water. So it doesn't like water, so we call that the hydrophobic end of soap. Hydrophobic. Phobic here means, of course, fearing. Hydro means water. So this end here does not like water. This end here of the fatty acid salt is a salt, as you can see here, a positive and a negative. Since it's a salt, it's ionic, so it loves water. So this end here is called the hydrophilic end. Why hydrophilic? Philic here, of course, as you know, means loving. And of course, hydro means water. So this is the water-loving end. If put in water, the hydrophobic end will form little micelles, just like this. And the hydrophilic end, which loves water, will be like this. So the way this works is that you get soap, and you put it in water, and you put your laundry in. This end here, which is described as your hydrophobic end, surrounds oil and dirt in your clothes and literally takes it out in that dissolved grease micelle right here. And once it's dissolved in that little trap, so to speak, then of course when you rinse your clothes, that comes off. So the dirt comes from the clothes and it becomes clean. So that's the way soap works, because there is a hydrophobic end and there's a hydrophilic end. The hydrophobic end will dissolve the grease and dirt in your clothes, and the hydrophobic end will dissolve in water so that it can be washed out. Here's another concept. You will notice sometimes that whenever you do your laundry, sometimes there's a scum on the outside of the container. And sometimes we say, gee, that was very dirty. But sometimes it's not. It depends on the water that's used. If you get water that's typically well water, it's described as hard water. Why hard? Because it contains lots of ions, minerals, such as the calcium, 2 plus magnesium, and iron. Notice it's all charged here. So it's a cation. So in the presence of soap, it will react with these ions here in water before it even reacts with the dirt in the clothes, and forms a product here. And this product here is insoluble in water. So that's your scum. That's on the side of the container. It's not your dirt, but it's taking out the minerals that are in water. So if you have hard water that's used for your laundry, typically you have to use more soap than if you used soft water. Let's look now at the properties of carboxylic acid. So here is the carboxylic acid, and just remember here that this end is the carboxylic acid end. All of this right here is the carboxylic acid. So what's stated here is that if there is an electronegative atom that's close to this group right here, this acid is strong. If you take the same electronegative atom and put it further, we have a weaker acid. We won't go too much into why, but just remember that if there is an electronegative atom that's close to the carboxylic acid functionality, it is strong. And if the same electronegative atom is placed further, then it's a weaker acid. Similarly, if we have a lot of electronegative groups bonded close to the carboxylic acid end, it's a strong acid. So let's look at this one, trichloroacetic acid. Here's the acetic acid functionality, or the carboxylic acid functionality. Here are 3 chlorines that are bonded to the next carbon. That makes it a strong acid. Over here, here's the carboxylic acid functional group again, and this has 3 hydrogens, not as electronegative as chlorine, so therefore this is a weak acid. Of course, we know it's a weak acid because it is acetic acid. You will recall that the pKa scale is used to measure the strength of acid. The more positive the number, 0.75, is a strong acid, and of course the more negative number, or the larger positive number here, represents a weaker acid. So conclusion, if there is an electronegative atom close to the functional group, it's a strong acid. If the same electronegative atom is further from the functional group here, it is a weak acid. If there are lots of electronegative atoms close to the functional group, it's a strong acid. And of course, if there are electropositive or less electronegative atoms close to the carboxylic acid functional group, that's a weak acid. Let us turn our attention now to the reactions of carboxylic acid. Looking now at the reactions. So, here is carboxylic acid. An example here is benzoic acid. That's the name of this acid here. It's termed an acid. So let's define an acid again. An acid is a proton or hydrogen donor. So here is the hydrogen. If this molecule gives up this hydrogen to a base, here's a base. If it gives it up to a base, this is an acid. So an acid is a proton donor, a base is a proton acceptor. Proton here is hydrogen. So let's look at this reaction. Benzoic acid has this hydrogen, After the reaction is done, the hydrogen is not here, but replaced by Na+. That's a salt. And let's look at the OH here. The OH that's here grabs this hydrogen and forms water. Of course, as you know, an acid-base reaction in chemistry is a reaction that gives salt, here's the salt, and water as the product. So benzoic acid, carboxylic acids are acids that will react with a base to form a salt and water. Here's another example. Ammonia is a base. It's going to accept this hydrogen here to form NH4, and of course that's your salt. There's no water here because water is the solvent. Let us look at another reaction, reduction. Let's define reduction and then let us apply that definition. Reduction is the opposite of oxidation that we have done in the previous chapter, which is the removal of oxygen. For us in organic chemistry, though, another definition is more important to us, and that is the supply of hydrogen. In organic chemistry, hydrogen is supplied as H-, known as the hydride ion. And we have seen that before in the previous chapter. So let us look at the reaction here. Here's a carboxylic acid. Here's the reducing agent, lithium aluminum hydride. Notice H4. So it gives up a lot of hydrogens. Therefore, it is a reducing agent. It's a two-step reaction because we'll have to neutralize it after the reaction is done. But when the reaction is done, the oxygen is lost. One of these oxygen is lost, and we have here two hydrogens. Here are the two hydrogens. So let's trace this reaction. Here's that carbon of the carboxylic acid right here. Here it is right here. This carbon has now two hydrogens from the lithium aluminum hydride, which means it's a reduction, and it has an OH. So this is a primary alcohol. So, conclusion. Carboxylic acids are reduced by reducing agents such as lithium aluminum hydride to form primary alcohols. Again, you may wonder what is ether. That's the solvent. So lithium aluminum hydride mixed in ether, which is a solvent, carries out the first reaction, and then a second reaction is with water. Bottom line is here we have the primary alcohol. Let us look at another reaction, and I think this is the last type reaction before we conclude, and this is called the esterification. That sounds like a big word, but let's define it. It's really the formation of esters. So it is a reaction that produces the ester functionality. We tend to associate names with a reaction, and this is Fischer, a chemist from years ago, who first discovered this reaction, so it's known as the Fischer Esterification. Here's how it works. So here we have acetic acid. Here's the acid functionality right here. And here is an alcohol, in this case ethanol. The reaction in a catalyst, sulfuric acid, takes off the OH and the H from alcohol to form water, as shown here, and here is the ester functional group. So that's called esterification because it forms an ester right here. I should point out that in a practical sense, because we'll see that these type reactions are very important to make esters in industry. So the way this works, because it is a reversible reaction here, based on Le Chatelier's principle, you can get the reaction to go to the right to produce a lot of esters by taking off water, evaporation. So as the reaction proceeds, we evaporate water and then we produce a large quantity of the ester. Here's just another description of it. So here's an alcohol and here's the carboxylic acid. The reaction in a catalyst such as sulfuric acid takes off H from the alcohol and OH from the carboxylic acid to form water and an ester right here. So here's an ester molecule. Esters are very important in the flavoring industry. As you can see here, these are all esters here, and some that you will recognize. Here is one, and it's the aroma and flavor of banana. Here's another one, that's the aroma and flavor of rum and orange, apple, etc. As I mentioned earlier, these are very important in the flavoring industry because these esters can be made from a carboxylic acid and an appropriate alcohol to form the ester. For example, this one is made from formic acid and ethanol. So here is the acid group and here is the alcohol group. So you should be able to recognize the alcohol and the ester that go in to make these different esters over here. And of course the process there is known as esterification, and the chemist who first did that reaction was Fischer, so the name becomes Fischer Esterification. This is the end of chapter 18. I know it's a lot, but it's chemistry that we are familiar with. The nomenclature is a systematic nomenclature. The reactions of carboxylic acids are similar to what we've done before, acid-base reaction. So again, as we progress in organic chemistry, hopefully by now you're seeing that it becomes easier because we can better put the pieces together as part of our knowledge in chemistry. So once again, as I usually conclude by reminding us that we're here not just to learn the content and the facts of organic chemistry, but we're here to utilize this information or the process to solve problems so that we can become and we are becoming better problem solvers and of course better scientists. So continue to study hard. We're almost at the end of the semester. So keep working hard and I'll post more information on D2.